Why do we etch? Lithography is the most charismatic part of the semiconductor manufacturing process, and yes, it significantly drives continued semiconductor advancement. But all lithography does is transfer the chip design onto the photoresist-coated wafer. That is it. Job's not finished. We still have more to do. We still need to engrave that design into the wafer's layers. That is what etch is for. We use a liquid or plasma gas etchant to remove the parts of the chip design we don't want and bring it to life. In this video, we're going to look at the long history and technology behind semiconductor etch. But first, I want to remind you about the newsletter. Sign up for updates and new analysis, the full scripts to selected popular videos, and more. The sign up link is in the video description below. I try to put one out every week, maybe two. Alright, back to the show. In the beginning, there was only wet etch, and this is how it worked. Semiconductor manufacturers dunked the wafer into a heated $10,000 quartz bath full of acid chemicals. What that acid chemical was depended on what we were etching, perhaps bare silicon or silicon dioxide on the wafer, or maybe aluminum layers they use for producing interconnects. It depends. Then we shake it. We shake it like a Polaroid picture. The shaking helps bring more fresh etchant solution to the wafer's surface. It also helps loosen any gas bubbles formed by the reaction. Bubbles prevent the etchant from reaching the wafer, slowing down the etch rate. After the etch is complete, we wash off the acid, dry the wafer using a spin dryer, and then move on to the next step. We want our etching rates to be as high and consistent as possible across every wafer and every run. But the process can only go as fast as its slowest step. So if the etch rates deviate from expectation, then something is wrong and we need to troubleshoot, like maybe we haven't shaken loose enough bubbles. Eventually, people switch from simply dunking wafers into a bath, the fancy word for this is immersion etching, to using a spray. This allowed us to bring a more continual supply of fresh etchant to the surface. Wet etching is a chemical reaction, which is its greatest upside and downside. One of the major upsides is that a chemical reaction is selective. With the right etchant, you can etch one particular thing without worrying about it etching any of the other layers. But a chemical reaction can be difficult to consistently control. It is also hard to automate, which means its effectiveness and yield is largely dependent on the individual operator's skill. And environmentally, there are particle contamination and toxic waste concerns. Some of these acids and their byproducts can get really nasty and cause pollution. However, wet etch's most significant issue was that it could no longer keep up with the shrinking resolutions dictated by Moore's law. Let me tell you why. A chemical reaction etches in all directions, vertically and horizontally at the same rate. We call this an isotropic etch profile, iso meaning equal. The big problem with isotropic etch is that we cannot guide it in the proper direction. And if you're not careful and the lines on the resist patterning are thin enough, then isotropic etching might cut entirely underneath those lines. This undercutting hurts imaging resolution. Undercutting first became a serious issue at the 5 micrometer process node, used for producing 16K DRAM. The industry decided that wet etch alone cannot achieve the necessary resolution for the next node, the 3 micrometer/64K DRAM. These concerns eventually pushed the industry to explore the notion of dry etch, an etching technique that does not use these wet chemicals. In 1967, a researcher at the American semiconductor company Signetics named Steve Irving, no relation to Kyrie, demonstrated the use of gas plasma to strip off a layer of photoresist from a silicon surface. This methodology is called ashing, so called because it essentially reduces things to ash. The concept is not new. People have been using gas plasma to ash the organic parts of animal tissue so that they can get inorganic stuff for testing. In an interview for an article gloriously titled "Cool Stripper," Irving said, "Photoresist material is nothing but organic material, and I had remembered from college that when we were looking at trace elements in diseased human tissue, we had the same problem of removing the organics without volatilizing the elements we wanted to look at." He purchased some plasma equipment from Tracer Lab, a subsidiary of LFE Corporation, to run his tests, and those tests successfully removed the photoresist without destroying the crystal structure of the underlying wafer. Plasma is the fourth state of matter. The plasma we use for plasma etching are ionized. This means the gas atoms become charged by either losing or gaining an electron, creating ions. When a significant percentage of the gas atoms become ionized, then we have a plasma. The sun is made up of plasmas, and they do fusion research with plasmas heated up to incredibly high temperatures. But the plasmas we produce for semiconductor production are not like those plasmas. We create them by exposing gas not to high temperatures, but rather a very powerful radio frequency field, usually 13.56 megahertz. The interesting thing about these low temperature plasmas, which are still pretty hot at about 50 to 250 degrees Celsius, is that materials react to them at lower temperatures and energies than if they were in their gaseous or liquid states. For instance, carbon tetrafluoride, or CF4, we want to use it to etch a layer of silicon. This layer is made up of silicon-silicon atom bonds, which are quite strong. So if that carbon tetrafluoride is in its normal gaseous state, then it can't do anything to that silicon layer. No etching will happen. But if we convert the CF4 into a plasma, we change the dynamics. A plasma state breaks those carbon fluoride bonds. The CF4 breaks into a bunch of fluorine, carbon fluoride 3, and carbon fluoride 2. And if we bombard the silicon surface layer with ions, the silicon bonds also weaken. Now, suddenly it takes much less energy to get the carbon and silicon to swap with one another. The result of the swap is a silicon tetrafluoride gas and a layer of carbon where the silicon had once been. The silicon fluoride gas can be pumped away. Now, what to do about the layer of carbon? If we pump oxygen into the chamber, it reacts with the carbon to create carbon dioxide. Once that carbon dioxide goes away, we have another layer of silicon atoms below for more etching. We start again. In 1971, Steve, not Kyrie Irving, received a patent for the process of gas plasma vapor etching. After that, Irving left Signetics to join International Plasma Corporation, where he developed the first plasma etch process for silicon nitride for making LED screens. The first plasma etch equipment were crossovers. They came from other industries that individual semiconductor people modified for their own purposes. But it was not long until the first specialized plasma etching equipment emerged into the market. The first such machines came in around 1972 and were called barrel-type reactors, because their main plasma reactors were in the shape of a barrel. On the outside of this barrel chamber are coils which will generate the high-powered RF field. They put these coils on the outside to prevent contamination. To use the machine, we stick the wafers into the barrel chamber like dishes in a dishwasher. The etchant gas mixture then goes inside and we turn on the RF coils. Simple as that. Despite these seeming breakthroughs, plasma technology did not immediately take off. By 1975, the entire market was estimated at only $1.6 million in size. Steve Irving recalled that most potential customers thought that plasma etching was for the healthcare field, not semiconductors. This attitude was justified. At the time, barrel etchers did not perform very well outside of their original purpose of photoresist stripping. In that, they did quite well and are still used today. When it came to actual etching, the product fell short. The barrel machines were very simple. They did not have good temperature control, they did not etch uniformly across the wafer, and the wafers themselves often suffered radiation damage. Most importantly, plasma etches of this first generation used chemical reactions, which meant that they were still isotropic. This isotropic profile disqualified it as a credible replacement for wet etch equipment. In 1973, Alan Reinberg at Texas Instruments decided that enough was enough. He ditched the barrel and tried something new, inspired by his work in chemical vapor deposition, the parallel plate reactor. I've also seen it called the radial flow reactor. This new design put the wafers on a platter with an RF-powered electrode underneath them. The wafers surround a hole at the center of the platter for gas to come in and out of, hence why it might be called a radial flow reactor. Above the wafers, we have another set of electrodes. Together, the two RF electrodes can convert gas into plasma. We can then use the RF electrode under the wafers to accelerate the ions in the plasma down towards said wafers, physically bombarding them. This will at the same time trigger a chemical reaction between the etchant plasma and the substrate. The benefit is that we can still get the selectiveness of a chemical reaction while guiding the etch in a single direction, something called Anisotropic Etch. The original parallel plate setup has since evolved into what is more widely known as the reactive ion etch system, which I mentioned in a previous video. Unlocking anisotropic etch unlocked plasma etch's full market potential. In 1975, a team at IBM led by Dr. Hua Nianyu, who later worked at Taiwan's ITRI, produced an 8 kilobit memory with line dimensions of 1 to 1.5 micrometers. The team used cutting-edge technologies of the time, electron beam lithography to transfer the pattern, and then reactive ion etch and ion implantation to etch the chip's features and give it its electrical properties. The demonstration made clear the future. Semiconductor manufacturers quickly transitioned from wet etch to dry etch, but with that, they came across two significant issues. The first involved the plasma damaging the silicon substrate and leaving residual impurities of metal or whatever have you on the substrate after finishing the etch. These damages and impurities need to be removed, so fabs added a post-etch step to do so. Post-etch cleansing might be done by blasting the damage with oxygen or hydrogen plasma, followed by a dousing of wet acid, followed then with a good old-fashioned hot bake. Or they can use lasers, which to me should always be the preferred choice, especially if those lasers are mounted on sharks. The other significant issue had to do with the equipment themselves. They were too slow. The first barrel-type etch tools might not have done good etches, but they did process wafers in large batches. Process batching lets the fabs make wafers faster. The transition away from the barrel gave us better etch precision and accuracy. However, these early machines, reactive ion etching in particular, could only do them one at a time and very slowly, hurting throughput. Since these tools easily cost over $1 million each, which was a lot back then, the fabs could not economically justify the expense unless throughput improved. So the etch tool makers either needed to get back to batching or speed up these single wafer jobs. Throughout the early 1980s, American and Japanese semiconductor companies tried to improve the latter by looking for ways to increase the density of the plasma. The first candidate was called Magnetically Enhanced Reactive Ion Etch, or MARIE. It is exactly as the name says. Very similar to the traditional reactive ion etch system, but we add a magnetic field to intensify the plasma and enhance the etch. It kind of worked, but the magnetic field's position parallel to the wafer created non-uniform plasma, which in part nullified its effects. So just rotate the freaking magnet, am I right? But doing so damaged the wafer, so MARIE turned out to be a bit of a dead end. In the 1950s, the Oak Ridge National Lab in Tennessee, America's leading nuclear power and hot chicken lab, invented a new method called Electron Cyclotron Resonance, or ECR. ECR was originally designed for fusion research. It uses both microwaves and magnetics to first produce high-density plasma in a separate chamber before we move it to the wafer. The Americans invented ECR, but the Japanese adapted it for semiconductor production. In 1982, NTT filed a patent, which they then licensed to Hitachi. Hitachi rebranded it to microwave plasma etching and used it for their 4 megabit DRAM at the 800 nanometer node. Throughout the late 1980s and early 1990s, Semitech funded Oak Ridge's efforts to commercialize ECR as well, but they eventually fell out of love with it. ECR was too complicated, you needed a huge magnetic coil which took up space, and it lacked uniform etch rates. So, in the late 1980s, they came up with a modification called Inductively Coupled Plasma, or ICP. You put the magnetic coil at the top of the chamber to produce high-density plasma using electromagnetic induction. ICP became the industry's dominant way to do reactive ion etch with high-density plasma. Applied Materials, Lam Research, and other vendors continue to work on new ways to increase the plasma density of the tool without damaging the wafer. Advancing etch technology is a key contributor to Moore's law. For instance, deep reactive ion etching, which is an etch technique descended from reactive ion etch and the MEMS world. You know I love MEMS. MEMS artists wanted to cleanly, quickly produce complex geometries in the silicon, like deep holes, for something like a tether beam. Existing etch methods fell short because their holes were V-shaped. So, in the 1990s, the MEMS department of the German company Bosch developed what is now called deep reactive ion etching. Their specific flavor of it is named after them, the Bosch process. This is pretty interesting. The Bosch process cycles through two steps of adding etchant and then an inhibitor to the substrate. Each step lasts for a few seconds. Let's imagine a flat substrate of silicon. Then we fire a high-density plasma mix of etchant and ions down at it. This is just the same as reactive ion etching. The ions physically bombard the silicon while the etchant chemically reacts with it. The etchant gets to work. Because it is chemical, it is isotropic, eating in all directions. This creates a little round crater. Then in the next step of the cycle, we apply the inhibitor, something kind of like Teflon, onto the crater. It coats the crater, nullifies the acid, and stops the reaction. Now we fire the etchant plus ion plasma mix again down at the crater. The ions physically break through the nullifying inhibitor layer, exposing the silicon surface at the crater's bottom for the acid to react with. But only at the bottom. Because those ions were fired in a single direction, downwards, the layers of the inhibitor on the sidewalls were untouched, so they keep the acid from eating into the sidewalls. This way, only the bottoms of the crater get scooped out. Over the span of many cycles, you get this deep hole in the silicon with a characteristic scallop sidewall. It's wickedly brilliant. Deep reactive ion etch is used to produce through-silicon vias, or TSVs. TSVs are one of the cornerstone technologies behind modern die-stacked chips, like our NVIDIA AI accelerators. We also use them to excavate the thin and deep trenches necessary for leading-edge DRAM chips. As Moore's law progresses, etch faces the same challenges faced by lithography. Simply put, we need to get smaller. Smaller while also being more precise. Oh, and it also still needs to be fast. So what does the future hold for etch? Atomic layer deposition is a well-established nanotechnology method to deposit very, very thin layers onto substrates. I did a video about atomic layer deposition a while ago. Go check it out. If atomic layer deposition builds up layers atom by atom, then atomic layer etching does the conceptual opposite. It tears down thin layers atom by atom. Easier said than done. ALD is already widely used on fab floors, but we are still working through ALE's quirks. I will save this juicy topic for a future video, but the work is a sign that etch, lithography's unheralded sibling, still has a vibrant future ahead of it. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the newsletter, and I'll see you guys next time.